Thank you, Professor Finocchino. I'm Kosuke Tatsumura from Toshiba Corporation. I'm very pleased to have this opportunity to speak to you all today. The title of my talk is Autonomously Synchronizable Multi-chip Architecture for Ising Machine based on Simulated Bifurcation. This is the outline of my talk. Simulated Bifurcation, SB, is a new quantum-inspired algorithm that we presented 2 years ago to solve combinatorial optimization problem. In this talk, we review our recent works on the simulated bifurcation with an emphasis on the scale-out architecture for Ising machine with full connectivity that allows continuous performance enhancement by connecting multiple chips. So let's start from the introduction. Combinatorial optimization problems are economically variable but computational hard to solve. The problem, these problems aim to find a combination of discrete value that minimizes the cost function of the discrete variable. Many problems for enhancing the productivity in various application fields can be mathematically formulated to the combinatorial optimization problem, including routing, allocation, placement, and scheduling, and so on. Many of those problems belong to the non-deterministic polynomial time, NP-hard class. The computational complexity scale exponentially with the problem size. A standard approach so far has been simulated annealing, SWA. Recently, special purpose hardware devices for quickly solving combinatorial optimization called Ising machine have attracted intense attention because of their possibility for substantial speed up. After the appearance of D-Wave's quantum annealer in 2011, various Ising machines have been presented, including CMOS data annealing, optical Ising machine like CIM or SPIM, coupled oscillator, memoristor, neural networks. The situation is very competitive. In 2019, Toshiba presented a new algorithm, simulated bifurcation, and its hardware implementation, which is called simulated bifurcation machine. A simulated bifurcation is a quantum-inspired algorithm, which it was derived as a classical counterpart to the quantum adiabatic optimization method named quantum bifurcation machine. One of the remarkable features of the SB is the plentiful parallels in the algorithm. The amount of computation is not so different from simulated annealing, but the parallelism of SB is outstanding, providing opportunity of substantial speed up by massively parallel processing. In this talk, I'd like to talk about a scale-out architecture for Ising machine that allows continuous scaling of both machine size and computational throughput by connecting multiple chips. First, I quickly review the mechanism, performance, and application of SB, and then move to the scale-out architecture. To our best of knowledge, this is the first study reporting a scale-out architecture for the Ising machine with full connectivity, with all-to-all spin-spin coupling. So simulated bifurcation. First, let me explain the Ising problem and the Ising machine. The Ising problem is the ground state search problem of Ising spin model, which consists of binary variables called spin interacting each other. A target combinatorial optimization problem is mapped to the coupling coefficient matrix J and bias coefficient vector H. Ising machine searches for a spin configuration S that minimizes the total energy of the system defined by this expression including 2 body time and 1 body time. The energy minimum spin configuration corresponds to the solution to the target problem. The Ising problem belongs to the NP complete class. Hence, by definition, any NP problem, including many combinatorial optimization problem, can be converted to the Ising problem with polynomial time overhead. The story of the birth of SB would be interesting for you, I think. My colleague, Dr. Hayato Goto, is a quantum computing scientist and has been studying the quantum computer for over 20 years. Quantum bifurcation QB machine by him is a quantum optimization method based on the quantum adiabatic theorem, which works only in the quantum world. When he presented the QB machine, he also presented a classical version of QB machine called classical bifurcation machine, CB machine, just to clarify the advantage of quantum effect by comparing the QB and SB machines. The simulated bifurcation was derived from the CB machine by adding an algorithmic twist for speed up. Why does the SB works well even in the classical world where the quantum adiabatic theorem doesn't work? There was no guarantee. We just found that the CB works very well and has an outstanding characteristic, that is parallelism. After the finding of the SB, we investigated the mechanism of SB. This is it. This slide shows how simulated bifurcation works. In SB, an n-body system dynamically searches for a good solution. In this figure shows the movement of the system in n-dimensional space, where the state of the system can be represented by a single point. In this case, the number of spins n is equal to 2. The horizontal axis and vertical axis shows the position of the spin variable x1 and x2. And the color map shows the potential. At the beginning, the potential has a single local minima at the origin. And then the time evolves, the potential gradually changes to have multiple local minima, approaches to the shape of the target cost function. There are 4 local minima: up, up, down, down, up, down, and down, up. The system is initially set up to be around the origin. Then as the potential evolve or the bifurcation happens, the system chases one of the minima, finally finds the best solution at -1 and -1. This mechanism is called adiabatic search. Moreover, SB is not a local search. If there are multiple minima in the energetically allowable region, the system can find the better one with better probability. This mechanism is called ergodic search. If n is large, SB finds a global minima or a local minimum close to the ground state from among 2 to the power of n local minima. This is it. The figure shows the position of n spin variable as a function of time. Each spin variable starts from the origin, then move to one of -1 or +1. Here, some spin variables exhibit very complicated behavior as many-body interaction changes every moment depending on all the other spin. The whole system approaches to one of good solution as indicated, Ising energy decreasing as time evolves. By fully utilizing the parallelism in the SB algorithm, we have developed a massively parallel accelerator for SB. In this FPL90 paper, we presented an implementation of our SB accelerator with full spin-spin connectivity on an earlier 10 Intel FPGA for the benchmark problem, complete graph max cut problem. The implementation support up to 4096 spins. It has 8,192 MAC processing elements. Their activity is 92%. That is 8K processing element do effective work, effective calculation for 92% of time. In the FPL paper, we compare the FPGA SB with the state of the optical Ising machine, CIM. It is optical Ising machine. It's substantially outperformed the conventional simulated annealing SAA in terms of the time to solution for the large scale 2000 spin max cut problem. FPGA SB has computational throughput of 1,873 gigamax per second, can reach the standard energy 4 times faster than the SIM. And the power consumption of the FPGA SB is only 49 watt, much smaller than 1000 watt of SIM. In terms of the energy per solution, FPGA SB is 288 times more energy efficient than SIM. As an application of FPGA SB, let me quickly introduce an ultra-fast financial transaction machine for cross-currency arbitrage, which was presented in this ISCAS 20 paper. This is an end-to-end FPGA-based arbitrage system where the feed handler captures a market feed, FPGA SB accelerator searches for an optimal arbitrage transaction path from all possible paths. Then the line handler issues the order packet. The system-wide response time from the market packet arrival to order packet issuance is less than 30 microseconds. This slide shows how the system responds to rapidly changing real market on January 2nd, 2019. The right figure shows the profit rate of arbitrage path. Red marker corresponds to the profit rate of the path by found the SB-based arbitrage machine. Blue lines show the profit rate of all possible paths prepared by the brute force method as a verification digit. The red marker positions on the top of the blue line, meaning that this system can find the optimal arbitrage path from a tremendous possibility in real time. The probability of the finding the most profitable path was 90.96%. Okay, let's move to the next section, scaling out Ising machine with full connectivity. There were the size limitation issue for FPGA SB accelerator, which strongly motivated us to pursue the scale out architecture. The machine size of single FPGA accelerator for SB presented in this FPL paper was limited by on-chip memory, which is needed for supplying sufficient data to tremendous processing element. The capability of the financial transaction machine was limited to fully connected 60 asset problem. That is a market graph with 60 nodes and 256 directed edge. What can we do if we want to take more assets into account? We want to achieve both enlarging machine size and enhancing processing speed. In other words, we want to enlarge the machine size while keeping the computational efficiency. For increasing computing performance and scaling, there are two approaches, scaling up and scaling out, making a chip larger or denser, otherwise increasing the number of chips. We choose this scaling out approach. It enables continuous enlargement of computing scale. However, it needs we need to develop a cluster architecture to avoid the performance saturation due to communication overhead. And for designing the scaling out architecture, we have to partition the spin system. At that time, spin-spin coupling over the subsystem must be incorporated, and the partitions subsystem also have to evolve in a single time domain. Communication and synchronization between the chips can easily degrade the speed performance, and this difficulty is more pronounced for the all-to-all connected network, which of more practical value than sparse one. We want to scale out the fully connected spin system. And for scaling out the Ising machine with full connectivity, we developed a multi-chip architecture for SB that enables continuous scaling of both machine size and computational throughput, which was published in Nature Electronics this March. It is a bidirectional ring network cluster without any centralized feature. All chips are homogeneous, autonomous, homogeneous, and symmetric. This is a photo of the 8-chip cluster, and it relies on an autonomous synchronization mechanism instead of using clock sharing or central hub. All chips are allowed to be launched independently with some time differences, but can be synchronized autonomously through exchange process of spin information between neighboring chips. Before explaining the architecture, let me show first the scaling out characteristic. If we may sacrifice the speed performance, it is easy to enlarge the machine size by connecting multiple chips. So the point is the scaling characteristic of the computational throughput speed. These two figures show the throughput as a function of the number of chips, P chips. Left figure is a strong scaling characteristic where we increase the number of chips at a fixed problem size N. For a fixed problem size, we can maximize the computational throughput by increasing the cluster size under an ideal upper limit determined by the problem size and communication problem. By minimizing the communication overhead with the autonomous synchronization mechanism, we have confirmed the throughput enhancement to the vicinity of the ideal upper limit. Right figure shows the weak scaling characteristic, where we increase both the number of chip and problem size in the same proportion. In this case, we can keep the computational efficiency constant. Moreover, in this paper, we have demonstrated the constant efficiency scaling at the maximized computational powers, that is at the strong scaling limit here. Finally, I'll explain the multi-chip architecture. First, we have developed a partitions SB algorithm that can be executed simultaneously on multiple chips. Each chip spin subsystem is responsible for updating N over P chip spins. Here, we have to pay attention to the fact that each chip needs to all spin information to update the N over P chip spin because there are all-to-all connectivity. The right figure shows the timing chart. There are two operational phases of communication and computation. In the communication phase, each chip shares all the spin information by repeating the exchange process of spin between neighboring chains. In the computational phase, the chips compute the time-evolved state in a chip parallel fashion. This slide shows explains the autonomous synchronization mechanism, which consists of local synchronization and global synchronization. Here, suppose there is a big time difference between chip K and chip K plus minus 1. When chip K is delayed, chip K minus 1 and plus 1 wait for chip K until chip K get ready, this is a local synchronization, which is achieved with a simple store mechanism related to the emptiness of communication buffer. Then the front of local synchronization propagate to the adjacent node via a symmetric ring network on every communication surface, achieving global synchronization. This we can realize the global synchronization without centralized control node, a choke point. This synchronization mechanism is simple but works very well. The requirement for synchronization accuracy is getting more and more severe as we increase the number of chips. This synchronization mechanism is realized synchronization accuracy required for the increased computational powers provided by the multiple chips, allowing all chips to fully utilize the computational resources in the time domain, eventually leading to the good scalability of the processing speed. In conclusion, simulated bifurcation is a quantum-inspired algorithm having plentiful parallelism, can be accelerated by massively parallel processing. We presented an autonomously synchronizable multiple architecture for SB, applicable to full connection Ising speed model that allows continued scaling of both machine size and computational throughput by connecting multiple chips. Finally, this is a reference list for the simulated bifurcation. If you like, I can provide this slide, so let me know. So that's all. Thank you very much for your kind attention.